This is just an overview video of what the researchers have been doing. It's kind of similar to our approach. So you just showing how the damage can be done. Okay. I don't know where the maximum value cannot be. Oh, the sound is not really good. No, it's only the projector, right? It's not the speaker. So it's on, but oh, wait, let me check. Still not clear, the sound? I'm not sure why it's not working. Let me just send you the file later, okay? Is that okay? This is just an overview from some researchers and how they do the experimentations. So they make sure the mechanical property. Okay. If you remember, I mentioned the tensile stress. That's one of the utilized characterization for mechanical property. Okay, let me just show you later. Okay, I don't know how this machine works. It's already on. Okay, so actually most of the content I took from one review paper It's the self-healing materials, review of advanced materials, evaluation, characterization, and monitoring techniques. As I mentioned yesterday, if you need some suggestions for your either homework or maybe the final presentation, you can discuss with me. Maybe you need some articles regarding some topics. You can email me. Okay. You can email me, and then maybe I can give you some advice or maybe link to some articles. So, in the recent trends, I want to include these three at least. Okay. Self-healing cement-based, anti-corrosion protection, and self-healing electronic. So I took these three because the first one, cement, is mostly used in constructions, and the problem is the cement or concrete, they are easily to be fracture brittle. So their life cycle depends on how prone they are to the fracture. Okay, and then corrosion. That's also one of the huge problem in industry. And then electronic. So if you have electronic devices and we want to make sure the maintenance for that device, so how to extend the lifetime, we can start by using the self-healing material. So self-healing cement based. Okay, so this is the reason. Okay, because it is really important in the construction material. Most of construction, they are using concrete, and the concrete itself is brittle fracture, and their durability is also not insufficient. Okay, under surface conditions. So how to extend their lifetime is we need to improve their property. So to improve their durability, sustainability, and resiliency of the infrastructures, the concrete itself, they need to be having the self-healing property. There are one video here, but I think you can watch after I've sent the file. This is just a simple video on how concrete could fix themselves. Okay, so basically, if you learn later in the civil and construction, you will learn maybe some concept on concrete. Okay, so concrete, they are consisting of, we call aggregate, right, and the matrix, we call the matrix or the cement. When we dissolve both in water, there will be a reaction. We call the hydrations, and it will become. If you see usually they are using, for example, in big like a dump, and they will rotate the machines, right? You will see this cement will be like a paste, right? So that's when they are dissolved and the hydration happens. So actually, the concrete itself, they actually self-heal themselves, but only a few percent. So the idea is how to extend or how to make the self-healing optimized. Okay. So the mechanism on how the self-healing cement works. Okay. First, it can be inspired by some animals, like a marine biology animals, any animals that have shell, right? So they are generating calcium compounds, okay, through bacterial activities. So if you see here, this is the bacteria activity. This is the cell membrane. This is the calcium compounds. Okay. So when they are exchanging the ions here, or in the cement process we call hydrations, they will create this calcium compound. Okay, so this is the lipid bilayer. Lipid means roughly it's fat, phospholipid. And the extracellular matrix is the matrix for the concrete. So by using the idea from the animals, we can also implement in concrete. So this bioconcrete in the real life, we can encapsulate the bacteria inside maybe some core shell structures, and then they will be activated when they are ruptured or when the cracking happens. So it's similar to the capsule-based self-healing materials, but the inside is bacteria. So these bacteria, they will work when they are absorbing the oxygen, and they will generate the calcium carbonate. And that calcium carbonate will seal the crack. Okay. So crack happen, and then the moisture will be changing because there will be at least water or air coming in, right? And then because of the reaction inside, the bacteria, they absorb the oxygen and they generate the calcium compounds. It has been, I think, developed quite well established, I think, the bacteria. Other method, I think the other method, this is what I can find. Autogenous healing is actually the concrete itself. So the concrete itself, without any additional chemical substance, it's already autogenous healing, but only a few percent, really small. But we can actually extend the concrete maybe with different chemical substance when we mix the concrete. And then encapsulation, like a bacteria before, here bacterial, but this is the using monomer or any additives to react with that monomer. And also using the shape memory material, maybe some kind of wire, so when the concrete broken, the shape memory material will remember the shape when it's triggered to some stimuli, and then it helps to recover the crack. But I think the shape memory material, the size and volume will be quite smaller than the other method. And then electrode deposition method, by applying the potential, the voltage, you can have an electrochemical process in which the electric or the current will deposit the chemical. It's also possible. So it's like in the corrosion, like in corrosion. So that's the self-healing cement-based materials. And this is for the corrosion. Okay. So by definitions, okay, the corrosion itself is the physical-chemical interactions between metals and the environment, and the result is the metals having the impairment of the function of metals. Okay, sometimes losing the functionality. And how to prevent the corrosions, the general solution is applying the coatings. So if you see some advertisement for painting, right, usually they have some chemical that, oh, it's waterproof, right? It's similar to that, and it's been applied really wide for oil and gas industry. Usually in a pipeline, they will coat the pipe, so when the fluids or the crude oil goes through that pipe, it will not easily damage the piping system. But the coatings, however, it is actually it will crack sometimes. Okay, it will crack sometimes. So if we can develop the self-healed materials on that coating, it will help a lot. Okay? And also, aside from self-healed coatings, we can also develop more advanced coatings, like a smart coatings. So the idea is still the same. They are using the microcapsule or healing agent, and then when the crack happen, see this is the crack, small, right? Usually it starts from the small crack. It's not from like the crack big at the beginning, but usually it starts small, and then it will be fracturized. It will be propagate. There will be a crack propagations. If you having interest in learning how material fail, there will be some really specific course, like learning how to make simulation for a crack. There's another whole course about that. It's interesting if you are looking for that, because it will be applied in many industry. Almost all manufacturing, oil and gas, they need to know how the material will fail. Okay. Like aerospace, it's prone to fail, right? Because we design the materials so that it can fly, right? So back to the system. So it's similar to the capsule base, but for the corrosions, the self-healing agent, it's not always self-healing agent. It can be inside this healing agent. Maybe you can also add some inhibitors. Okay. The inhibitors, it will at least slow down the corrosions. There are several inhibitions. It can be chemical substance or any maybe biology. Also, they can eat the corrosions. Yeah, you can say that. Yeah. And how they are contained inside the containers. The containers itself should be maybe porous, hollow, or layered structures. It can also be done. Okay. So inside self-healing agent or inhibitors, or maybe both, it can be done also. So because the healing agent, they need time to recover, right, to polymerize. So when they are react, or they need that time, maybe some substance already inside, and make way to the metals, right? So that's why you need inhibitors to slow down that process. And this is the self-healing process in another materials, but it's the same concept. Okay. It's the micro capsule here. So A, without damage, and B, you damage the system, and it will expose the metals. And here it's using the I think it's silane, alkoxylane. Yeah. So it's containing the alkoxylane mixture on a metallic substrate. So in the substrate, it has the alkoxylane. So it will be quite preventive. So if the metal's exposed, it will quickly create a layer in the metals itself. So
the idea is that if there is a crack and then like the material is actually react to the environment cracking, so it's gonna be healing itself.
yes.
Like what about the part of the material that is outside? Isn't it actually also react, and can it actually just make some substance so until like it doesn't look properly again?
Yeah. Actually, like the coating or any preventive actions in a design, we need to choose which sections that really prone to the environment, and that will be the top priority. So that will be the selection for how the coatings will be done. So like in here, okay, when it's damaging the system, it can be in outside system, it can be inside. It depends on how prone the design will be. It should be done in before the production. So when the design already in like a blueprint, they need to determine which part they need to make the coatings in. So like I don't think, like for example, like industry like the oil and gas, sometimes they don't need to have a beautiful looking design, right? At least the function's still running. But in other case, maybe designing some automotive, they need to have like a compact and beautiful design, right? That will be different case. But I think for corrosion, mostly it happen in the they need to make sure, because it's related to the cost effective. At least they need to make sure they will have optimized benefit from the process. Because if the corrosion happen and it will rupture the process or the damaging the design, it will, if they are off for maybe 1 or 2 days, it will be really the cost will be lost in billions. It's really, it's really scary actually. Because I have a lot of colleagues working in the oil and gas industry, and sometimes they were like stressed out because they need to make sure the system are working, and they usually if they are working on site, they will have like 2 weeks shift, like 2 weeks on the site, and then 2 weeks they will off and go, and they have a vacation. But I think they cannot now. they cannot have any vacation. They need to stay home, or they need to go to on-site. Some of my friends still go on-site because if they stop, then it will be bye-bye to the world. You know, like the electricity, they need to work. If they don't work, they don't have any electricity left. And maybe for the internet, right, connections and so on and so forth. Yeah. So back to the design. So the difference from here to the previous one. So aside from the polymerized agent inside this blue layer, they will have a layer in metals itself. So the metal itself, it has a layer. So when that layer exposed to the environment, it will quickly recover this green layer. So this green layer will be there, waiting for the blue one to be recovered. So this layer, we can call this layer as a passive layer or hydrophobic layer. because it can create this hydrophobic. If you see in any paper, any article, see like this red line like this, in a molecular, like a molecular structure like this, you see a red line like this. This red line indicating it's hydrophobic. But if you see, it's not red line, but after this red line, maybe like circular, maybe circular blue here. The circular blue is the hydrophilic. Okay. Remember the lipid that showed before, the phospholipid? It has the circular, it has the tail, right? The head and the tail. That's the hydrophilic and then hydrophobic. And then react, and then it becomes the passive hydrophobic. Okay. And the other method is this is the inhibitor. This is anode, cathode, electrolyte at the middle. This is the coating metals. So the coating, from that pigment, it can release the calcium ion, which later they will inhibit the process for corrosion. The corrosion process is actually the electrochemical process, right? So they are inhibiting the process because they will react. So instead they are react to go for corrosion, they will react by themselves and create like this calcium hydroxide. So instead corroding the metals, they will corrode themselves, the iron. Yeah. Okay, so the inhibition of corrosion-driven coating disbandment derives from the exchange of ions, these ions, calcium, ion. Okay, that's the corrosions. And then self-healing electronic, it's quite a good prospect. Okay. So if we divide some groups, there will be a sensor, electronic skin, supercapacitor, perovskite, solar cells, field effect transistor, battery. Maybe you are wondering what is perovskite. Is it someone name? Maybe it's someone name, but actually perovskite is a typical structure usually in ceramic. So the perovskite, how to explain? So if you remember, we have the in our materials we have unit cell, right? Unit cell, it can be cube, it can be face-centered cube, like the arrangement of the atoms. So perovskite is one of the arrangement of the atoms, but the side it's having displacement slightly off. So what does that mean? So when you give them electric or current, they will have some efficiency because of that off positions. Yeah, that's the simple way to describe. But I think maybe I need to show you later how the structure is. So it's usually using in the solar cells or any electrical components. Field effect transistor, battery. So the first one is conducting materials, because they are mostly used in all electrical device. They need to conduct the electricity, right? If not, the device will not run. So this battery, coating, supercapacitor, electronic skin, chemical sensor, solar cell. Yeah, solar cell. Yeah, this small solar cell. Coating, battery, yeah. So if we see the key development for the self-healing electronic device, I think some of the picture I already showed you before. So first is the conductive materials. So this is the nickel particle. it's supramolecular nickel particle, and this is the conductivity for that nickel. It depends on the nickel volume reactions, and this is the experimentations. So they are cutting the material, and then they will be connecting each other, and then they will check the conductivity, and it's lighting the LED light here. So if you see the microstructure, this is the damaged structure, and it's self-healed. So aside from checking the mechanical design and checking whether it's self-healed or not, you need also to check whether the functions still okay, the conductivity. And the other, this is the also similar, checking the conductive material. So it's having cut here, damage here, crack, right? And then self-healed, and then checking the resistance. It has some stimuli to check. We call the reversible bonds. Maybe more. Okay. And this is the hydroxypropyl methacrylate, PHPMA. Yeah, they usually, if you see that name. And then polyethylene imine, PEI, cut, and then healed. And this is healed by the hydrogen bonding here. As you can see, HO here. This is all hydrogen bonding. And this is the microstructure. Not microstructure, it's just optical microscope. Before cut, and then cutting, and then they are increasing the temperature. So the stimuli is the temperature. And then after 10 minutes, it's already the same as before. And they are checking the electrical property. So to make sure that it is performed, still okay to perform. Okay, not really 100% self-recovered, but at least it's still okay to perform. They have gap here, right? And then also the photo-switchable crosslink network formation. So if you see any HHV like this, meaning it's light. Okay? It's light with this wavelength, 365 nanometers wavelength. So some polymers, they have behave differently according to the light. Some polymers, or maybe the monomers, they will react with the other monomers in some wavelength numbers. Yeah, sometimes. And here it's showing the photodimerization of, it's called coumarin. Yeah. Yeah. What is happening? Yeah. So the pathway, the proposed pathway, so it's still the prototype. This is the agglomerated polymer, cleavage, and then giving the light, and then the contact of the coumarin of functionality, and then healing with the 365. So when 254, it will be having a cleavage, and then when 365, it's a crosslink. Or here is the molecular of each monomer, and then this crosslink, it's having this orange line here. Okay. And another example is the SelfHealing conductive composite. So it's like a flower, right? It's a cyclodextrin, and this tubular is SWCNT. It's called single walled carbon nanotube. What does it mean? So it's only having a single layer, and it's the carbon. All of this point is C. It's C. It's only carbon. So if we incorporate this cyclodextrin binding to the single walled carbon nanotube and incorporate this like, what is this? It's the hydroxy methacrylate. So see, it's having head and having tail, right? So it's hydrophilic, hydrophobic, and it's making a good pathway here, bind in this cyclodextrin, and all the carbon nanotube and cyclodextrin and these hydrophobe structures, they are interconnected, becoming a supramolecular network. So the research, they believe this structure will help to self-heal. So that's some other method. If we see the summary, they have incorporated some research from 2007 until 2017. Blah blah blah. You can read later if when I send you. But what you need to see in the important points, okay, what you need to see is the healing mechanism. Okay, you see here dynamic metal carbon bond. So they need to utilize metal carbon bond. Then non-covalent interactions and ligand, and then mostly they are using hydrogen bonding, pi interaction, electrostatic interaction, hydrogen bonding, blah blah blah, release of healing agent, microencapsulated salts, ion dipole interactions. But mostly hydrogen bonding is appearing here because hydrogen bonding is actually fast. They don't need really much time to react. It's different from covalent, right? The covalent is it's quite strong, right? Hydrogen bonding is weak, but it's helpful because you can control how they how the time will be. Okay, you can control that. And then self-healing sensors. Yeah, so sensors, they need to perceive any external signals, right? It can be physical, like the stimuli for physical, like light, heat, or maybe chemical substance like a smoke or any chemical that can be perceived by the sensors. So they are the basis to achieve the detections, the automatic detections. So the idea is if self-healing sensors utilized, we can increase the lifespan of any device that have the sensors. Both functional, the sensing ability, or the aesthetic purpose for the design. I think in the market, mostly they are available in like your smartphone case. There are some cases that are already built for self-healing purpose. So this is they are using humanoid here, but the important is they are using this red This is the self-healing tactile sensor, and in the arm, the robot arm, it's self-healing flexion sensor. And in the robot eye, they will have some reaction there. They will move the arms and see the reactions, and see the light in the body, it will turn on. So they check the light, they cut first, so it's only half turn on, and this is after healing, like a smiley face, right? So they check also the deflection sensor. And then the electrochemical device. So electrochemical includes in there the capacitor. So in here you have the supramolecular network, the spheres, the circle one here, we call this is the titanium oxide. Okay. So they made the self-healing substrate based on this structure. So they will put the substrate on this SW, the single wall carbon nanotube film, and they put several layers assembly like this one. So when does this device crack? Okay, before it is cracking until the deeper inside here, before it goes there, the substrate will self-heal. So it helps to maintain the device integrity. So A, B, C is the same profile, and D and E is different profile. So in D and E, here you have the fiber, the conductive network, breaking the materials. You can have inside of the materials, the wire is having the like a yarn, and then it has a magnetical property. So when it's broken, the magnet will attract between these two, okay, and then it will self-heal the matrix, help to self-heal the matrix. And then what's more, yeah, and also you can make a self-healing materials through printing. So you can print out the carbon ink. So this is the graphite, and then you can create a printing pattern, and then that carbon ink will help to be a template for a self-heal. Okay. So the idea is still the same. You have the healing agent, release the healing agent, and then healing the printed trace here. But you are making the template for the printing. Okay. This is the same as before, the magnetic attraction, yarn-based supercapacitor. So yeah, I think this part, the self-healing electronic, if you want to focus on this part, like in your homework or maybe final, you can think of incorporate in your paper or maybe in your final, maybe the functional test, like how good it is after the self-healing, like how many percentage the functions left. Like the ideal is 100%, right? But reaching, I think 80% is really good. Mostly they are reaching only 70 or 60, around that percentage, the function. So if you can maybe improve that with some idea when you observe in any paper, any articles, and you can combine them and making an improvement. I think that will be a good idea. Okay. Yeah, self-corrosion. Yeah, if you want to go cement, corrosion, or electronic for the self-healed, you can try that. Okay, so don't forget next week the second homework you need to submit, and then the next day, I think 21st the homework, right? And the next day will be the presentations. I will choose a random number. Okay. I think we can stop here, and I hope you can get many idea or improvement for the homework and the final.